Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at a project on biometrics activity classifier. So the data that we have in this video is collected from mobile phone, and that data will use to classify whether the person using that mobile phone or a smartwatch was walking, jogging, dribbling basketball, clapping, or folding clothes. So there this the data set is much larger than this, and it can predict um, about 18 different types of has different types data for 18 different activities, but we'll focus on just these five. And the talk is going to be fairly long, the video, so it's divided into three parts. First, we'll look at how to read and combine data from .arff file into DataFrame, and then we'll look at how to pre-process the data to get it ready for the prediction model. And finally, we'll write the code for the model and see what the output is, yeah, and what the accuracy is. The data source is listed here. Many thanks to the Wisdom Lab and UCI Machine Learning repository for providing this data as open source. I'll put the links for the data in the description of the video so you can download it from there. And in the zip file that you download, it's a large zip file, it's around 300 megabytes. So there is a PDF file in there. You definitely want to read that file to get an idea about what the data is about, how it was collected. So it's a nice paper that you can read and get an intuition about uh, how what's in the data. Now, this is a short story about what uh, the data is, or how the background behind the data. So in a mobile phone or in smartwatch, we have a gyroscope or accelerometer. So they both measure different items. So gyroscope measures the angular velocity and orientation, and accelerometer measures the acceleration. So these two readouts from the sensor can be collected, and that can be used to classify what particular activity a person might be into when for a particular data point. And so in this video we are going to look at if the activity is walking, jogging, dribbling basketball, clapping, or folding clothes. And you'll see as we'll do some visualizations that some of these activities, so most of these activities have x, y, and z coordinates measured. And the data set also has raw data, but we won't be working with raw data. We'll use the features that are already provided in the data set, and within those features then uh, you'll see that there are coordinates and there are other features derived from those coordinates that are measured. The data itself would look something like this. I have this created this folder on my desktop, and these are some of PDFs that I've downloaded. This is the zip file that you'll download, wisdom.dataset.zip, and once you unzip it, these are the actual files that you'll have. And this is the PDF paper that I'll recommend reading to get an insight into what the data is all about. And then there is raw data. We won't be using that in this video. We'll use the data that has the features already made. So those are in ARFF files. And so we have the data from phone, a device, and also watch. So in each of those two folders, there is readings from the sensor for accelerometer and gyroscope, sorry. And those files look like this. So part of the first part would be dealing with how do we pull this data into a Jupyter notebook, get into a DataFrame from, how do we combine that. And so let's look at the data now. these are the labels, as we already saw. A is for walking, B is for jogging. We are not going to be working on this, and I'll explain that while we write the code. We are working with dribbling, clapping, and folding. Now for data, the ARFF file looks something like this, uh, where we have these are the column names that are shown here, and below this is the actual data. So where it says ampersand data, so this is the data that's in the file. So we'll use a inbuilt library in Python to bring this into Jupyter Notebook. While we do that, I also realize that there are some uh, uh, points in the data set that we need to also work with. So as compared to the previous video on mushroom classifier, this is much different, because here the data volume is much larger, and there are the data, we have to process the data to get it to work. And while working through this, in some of one file came across this uh, issue where uh, the file name has a subject. I think that's the class ID 1611, and this is 1610, and the file has all 1610s in it. So we have to modify the code so that if there are any other files that have this discrepancy, then uh, we replace this by 1611, replace this by 1611 as well. So let's now get into Jupyter Notebook and see how we can write the code for this. So here again, we have the data source, which is from UCI machine learning repository and WISDM Wisdom Lab. Now for libraries, these are the libraries I've imported. There is a new library called plotly.express, and we'll use that for 3D interactive plots. Then I know that we have not discussed random forest yet, but I just wanted to bring that here to show you that what we are doing, working with right now are linear models, most of them, and random forest classifier is another way which is much powerful for certain types of data set, and it works really well here. So I just wanted to bring that in here. We'll discuss that in much detail in future videos. And this is the library we want, ARFF from SciPy, and we'll import that. We are also importing OS, because we'll be iterating through the directory to read each and every file for the data. And let me run these cells, and these are the versions that I'm using. So now for the data set, I've set the path here, uh, because that's where the file is downloaded on my computer. So the very first part that we are going to work with is read the data file. And so for this, work through the data. And so it took me much longer than what I'll be working on this video, typing the code. And the take a one kind of, I'd like to preface this video saying that the tools that we have in for writing the machine learning code is just one part of the actual implementation. The much bigger part is also gaining the intuition about the data, what the data is trying to tell, because uh, understanding that the data is very crucial. It's very important to create new features that could improve the accuracy of the model. So this would be a completely new experience as compared to the previous projects. So I hope you learn from this particular video. So for data, we'll first create a function. I'm going to create the functions as we go. So our first function is get ID, and from file name fname. And the reason why this is because the name of the file that we have, I'm going to split that and get the classes or device name from those. So if we go back here, as you can see, this file name is data underscore 1611 underscore axle underscore phone. So we can split this and get the axle and phone from the file. That's kind of the idea here. So return file name dot split and underscore and then 1. So when we are splitting on this and getting 1, we are getting this information 1611. That's the class for from the file name. So that's the first function. Then the second function is we are going to name it as clean file df, and this takes in file name in path, so path of the folder where the ARFF files are located, and then it will take out path where what we are going to do is read a file from the directory which we downloaded, and because we need to do some corrections while before we can use the data, we are going to write it in a different file, temp file, and then we'll read that back again uh, to read it into DataFrame. So this is something that I found out while working through this data. So it here it might appear that I found it uh, uh, very easily off the hand while looking at the data frame, but that's not the case. I've spent hours looking through the data. So uh, that's the practice you could do, is work with this data set uh, on your own and see what problems you find and how you can solve them, and then you could use this as a reference to the way you are trying to analyze this data. So the first item that we'll do in this function is get the ID. So num underscore ID is equal to get ID and file name. So that's, we are calling the function that we just created above, and then we'll read original file, and for this we'll open, so with open in underscore path r as file, and here we can read the lines. So read lines as list to f list. So here we are going to create a list of each of those lines, and the reason for that is we're going to edit those lines now. F list is equal to file dot read lines, and why we are going to do that is because if we go back to this, the library that we have in scikit-learn, when we run that library as is with the ARFA file, I was getting errors that this is incorrect, that S is not in this set, where it clearly is in this set. And when I removed this space after the S between the curly braces, that error got away. And then the second error was, in this particular case, there is a space before the before and after this particular number in here within the set, and therefore it was saying that this particular string does not match this string right here. And so that's what we need to fix, and for that this is the function that will do that. So add the new text in text to the specific lines. And here this line has a number 3, so 0 1 2, that's what we'll use. And then this is at 95, so this would be line 94 that we need to edit. And so f list, so this is the item that we'll pull from the list. This is the second index 2, and there we can simply copy this. So I'm going to copy this entire line, and what we'll do is we are going to replace it. So the existing line will be replaced with this line, and I'll put a new line character after that. Next is flist 94. So that's the other line that we talked about, which is this one. So I'm gonna copy that entire line and paste it here. Maybe within quotes. And here we do not need the, okay, so a couple of things happened here. So the first time when I ran this, my idea was to put this get ID in here. So that way it'll just replace the string with spaces without spaces. However, then ran into the problem where the file ID did not match with this particular string. And so the solution for that was then to just completely ignore this and rename this particular as numeric instead of this. So what I'm trying to do is say this is numeric and then manually put this number as a column into the data frame. Okay, so for that then we don't need this return, so I'll just say numeric and a new line. So that changes the arif file, but then I will add this information later. And then we're going to write this updated file to a temp file. So put the list of lines into a new file and with open out underscore path, and I've not specified the out path here, so that's going to be okay. So it doesn't matter. I will use, it will be as the input to the function, so we are fine there. And here we are going to write as file dot write lines, and this is flist, and then file dot close. Now we have read the file here, we have edited the file here, and then we have written the corrected file in a new as a new file. And now we are going to read the file, the clean file that we created. So read the above clean file, and this is data is equal to arff dot load arff out underscore path, and that's the library that we imported above. Then we convert that to a data frame, and let's call that temp data frame. So temp is equal to pd dot data frame, and this is data 0. And now we can we need the column name. So temp dot columns is equal to within the loop for x in temp dot columns. So what I'm doing here is when we create this data frame, another point we want to change in this is these column names have quotes around them. So the data frame would have the quotes in the column name. So if you pull the column name for, let's say, for xy cor, So that would appear like this, XYCOR, because the quotes is considered part of the column name, so we don't need that. And so that's why I'm removing the quotations from the column name here. So x dot replace will replace the quotes here with nothing. So that should fix the quotations in the column names. And then uh, uh, when we read this file, you'll see that a letter B appears near the activity. So if we say walking, the additional letter B appears. So to fix that, we need to type UTF-8. So we need to write that line here. Activity is equal to temp activity dot str dot decode, and you're going to use UTF-8 for this. Now after this, the next item is the data set. As you can see, it does not have file, so we'll add a file name, we'll add a sensor, and we'll also add the device. And the reason is, when we are reading files from different folders, it would help us keep track of what device or what um, sensor within which device the data is coming from. So what we are going to do is, to each of the data from these files, we'll add this Excel for that, maybe gyro for the file within this folder, and then watch or phone. And all that information for is available to us from the file name itself. So here we have the Excel and we have the phone. So that's what we are going to use here. So here this would be add. So we are going to add a file name and a sensor, device columns, temp.insert, and I'm putting them as a first three rows, first three columns, so that it's easy to see those. So location, so that's 0 index. Column, here we specify the column name, so that's f name is the file name. Value, so that's going to be just f name. Then temp.insert, the second column would be at location 1, index 1. Column in this is going to name the sensor. And again, now for this, the file name, we already have the file name. So what we are going to do is split this again on underscore, and then we will get 0, 1, 2. So that's going to be the index 2 after we split it. So split and this underscore, and then after that we going to get the second item on that list. And then temp.insert location 3 column, and this is device, and again the value is fname.split. We'll split this on underscore, and for device, when we split on underscore, the last item in the list would be phone.arff. So we need to split it again by the dot, and so we'll get the phone out of it. So we have 3 dot split, and then we split this again, and then we get 0. So that should give us the the 3 added columns in our data frame. And then finally, we need to fix that issue of class name. So we'll add that here, fix class name. And this is because, let me write that here. So because scrolling up, because class that is subject underscore id in some files does not match the file name, and that's the reason why we are doing this. And that is is a easy fix. What we'll do is just in that column we'll add the num id, and that should take care of that. And finally, delete the client file. So once we are done with getting all the information from the new file that we created above, we can go ahead and delete that. So the reason why we are deleting it is because if the data set is large, it will combine a lot more space, so we don't need to keep that. And then return temp, so that will return a data frame. So we are reading, this is f name, so we are reading the arfa file in this particular function and outputting a data frame. So that's the function we have. And the next, now we'll write the code to loop through the directory. So remember this, we'll enter these directories. This is going to be the root directory, and from this we'll step through each directory, subfiles, all of the files automatically, and then it'll magically give us a data frame with all the data. So let's do that. So here we are going to step through the data files in folders and subfolders. Okay, so that should be good. For this, we'll first rename a root directory, and in the computer where I am using, it's going to be this users, and then I'm going to have it on the desktop as the folder, and that's the folder from the zip file after it was unzipped, and then that's the folder which has the files that have features, not the raw data. And here I'm going to initialize a variable init as 1 and initialize another variable count as 0, and you'll see in a moment why. So for subdirectory and then directories files in os.walk root dir, and here we are going to, I'll go ahead and print each of these. So print subdir, and then subdir, then the next one is dirs, and so this is dirs, and then finally we have files. So files, actually the files in that folder files, and just have a new line there. Now you can run this to see the list. So here we have a subdirectory, the directories, and if there are files, the files within the directory. So the main files are in here, where phone, gyro, we have these files, phone accelerometer sensor, we have these files, we have watch gyro, and then watch accel. So we are going to read all these files, and the function above will do the conversion to a data frame. And here to separate these, let's add a dotted line there. Now within this, when we reach the directory, we need to iterate through the files. So for file name in files, this is where we are going to read the file. So if fname dot split and then underscore 0 is equal to data. Now what this line is doing is, if you see within that data folder, there are other folders or other files that we do not need, and such as this one. So this will check, it will split the file name on underscore, and if the first string is data, then it will proceed to read that file, otherwise it will skip it. So these are some of the uh, points in working with real world data, is that you have to work for every column and every row to get it in the form that you need for the model, as compared to the toy data sets where we can plug and play the models. Here I'd say you spend about at least half of your time just fixing the data, so that, or transforming the data so that it suits what you are trying to work with. And again, sorry, again, this is the path, out path. Maybe just copy it from here up to there. We have that, and within this, we'll name the clean file as clean file arff. And then, so our route is going to be, we first read the arff file, transform it or clean it, and then we put that in a data frame. And then that is what we'll get when we call the function clean underscore file underscore df, which needs input of file name, in path, and out path. And so once we have that, once we get the data frame out of that function, we need to save it. And to save that, we'll create a new data frame called dfmain. However, in the very first iteration, it's not going to be there. So if it's the first iteration, we'll save the temp as dfmain. So copy, we need to subtract 1, so init minus equals 1. So for the next iteration, then it won't enter that part of the loop. And then we have dfmain is equal to pd.concat dfmain and then temp. So now when we run this, it should go through all these files in these two directories and subdirectories, read each and every line, do the corrections, save it as a new file, read from that file, and put everything in the data frame, change the columns names of the data frame, add those 3 extra columns, and all of this now should be done with by running just this cell. So let's run this, and I will see, this was the previous run there, and it should give us all the rows that we are looking for in the data frame. So we have around 75,000 records, 75,099, and we have around 96 features. So we can also look at what the features are and what the, so if you type dfmain.columns, we can, so these are the columns. So these are the fname, sensor, and device. Those are those items that we added. I wonder why activity is gone there. So let's go back up and check here. So this should be 2 and not 3 and 2. So run this again. So we should have that in the index 2 before activity. And why don't we look at the data frame as well? So df.head 5, and we should see what the data frame looks like. So we have 75,099 records, 96 features, and we should see the column names and then first 5 rows of the data frame. Still running. And after that, while that is running, I'm going to go ahead and print df main dot sensor dot unique, so we can check if we have all the sensors So here now we have file name, sensor, and device. Then these are the actual original uh, columns, and then this is the last class column that we edited. So all of them are in here, and we don't have the quotations in the column names as well. So if we look through this, you can see that all the columns look good, and these are the columns that we could use later, or we can drop them, but at least we now have all the data ready for all the trials that we want to do. And let's look at the device dot unique, and this we have both gyro, axle, and then we have phone and watch. All of them are there. Now first item that we can look at is visualize the data. So visualize data, and for this we'll create a heat map of the xyz. So heat map by z, and the heat map would be what we already have above. So these coordinates right here, x0, x1, x2, x3, all the way up to x9, and then same thing for y up to y9, and then for z or z to z or z9, and we can plot them. So we can see the reason why I wanted to plot that is because while going through this data, initially the accuracy score was much low, and wondering why that was the case. So if you look through this data set, these values are 0, and there are a whole lot of zeros in these, and we can visualize those zeros and see if it will make sense to uh, get rid of the zeros, or transform the zeros, or transform the columns. So trying to explore the options, and this plot help do that. So figure is equal to plt dot figure fig size is equal to 10 comma 15. That's just the size of figure, and we're going to use the SNS Seaborn library heat map dfmain dot lock loc iloc. We'll use iloc so we can give the index. And as you can see, the index for this is we start at 0, 1, 2, 3, 4. So we start at 4. I'm going to add 1 plus 4, and then 30 plus 4, and cmap is equal to binary. And when we run this, we should get a plot that starts, oh, this should have been maybe 0 then. We'll rerun this again, and you'll see bands of, okay, so let's rerun this. We'll see bands of data for gyro and gyroscope, and then for accelerometer, and that was really helpful to see how the data is laid out in the data frame. So as you can see, this data which is gray color, so everything that is gray, darker the color, the values are closer to 1, and lighter the color, the values are closer to 0. So these are all zeros. So you can imagine how many zeros are there. So if you try to train a model with so many zeros, it's, the accuracy was much lower. So what you want to do is uh, either get rid of the rows that are zeros, or try to remove the columns that are zeros, or you can fill these in with transformed values, so that these could have some value. But while doing that, you also need to be careful, because those could be the actual coordinates of the position. So 0 is actually the correct value, and so uh, just trying to make sense of how the data looks like. This figure helped, and what I ended up then doing is, as you'll see, uh, try to remove the rows which had zeros. So ended up removing all these rows that were for gyroscope. And you can experiment with different variations of this. So this video could be just a tutorial on one way of looking at the data. There could be maybe hundreds of other ways, and you could explore keeping some data, removing other, or transforming the data, and hoping that this video will help you uh, find your own route in the data analysis as well. The next item for visualization is 3D. So let's do that. We'll look at X, Y, Z, the same coordinates in 3D. And for this, we'll use the library scatter underscore 3 method scatter underscore 3D. N is equal to string. So this is to simply create a string n because there are x0, x1. So what I'm doing is putting them so we have to type it every time. So in order to avoid that, just have that n that we can join as a string. dfmain and activity. So for activity, we are going to restrict to only those 5 activities that I talked earlier, and not all the activities that are within the data set. So I think it was A. So let's go back and check. It was A, B, P, R, S, and those are the activities that we'll look at. So A, we have B, then we have P, then we have R, and then we have S. And we can print this dd.columns. We can look at the columns, and then px.scatter underscore 3d dd x is equal to x, and then we'll specify the plus n. Y is equal to y plus n, and then we have z or z is equal to z plus n. And opacity, so here we cannot use alpha, you need to specify opacity, set it to 0.1, and then color would be based on activity, the type of activity, and the color would be different. So now when we run this, we should see a nice 3D plot. So these are the columns that we have in the data frame that we created here, the DD data frame. And this is a really nice plot, 3D plot that we have here. And in this plot, you can see how the data points are in 3D for just 3 columns that we have, just these 3 features. And we can see there's quite a bit of overlap. There are several points along the edges of this cube. So those are zeros. So these are on 0 for one of these axes. And there are some points in the middle, and there is overlap as well. So, and this is just for these 4 classes. If we have more classes, then that would change the picture again. So if I remove that filter and then run this, we should see so this is for all the classes, and you can see there's too much information in here that the linear model that we have learned so far in the series may not be able to do a good job of classifying these. So that's the reason why we are going to limit this to just these 5 classes. And even still within those 5 classes, we are going to remove some of the data to get a better prediction. And as you can see, these blanks here, those are the zeros that maybe they do not provide more information that the model can learn from. So removing them could improve the accuracy. So before we do that, I just wanted to show another visualization of this same, where we can add filters to remove those zero data points. So let's say we can create a list, and within this list we can specify here dfmain and x3 not equal to 0, and then ampersand and we'll type this out for all x's up to 9. So this is 4, so that would be 4, and then we have 5, 6, 7, 8, and 9. So let's type that. 5, we have 6, 7, 8, and finally 9. And then uh, getting that filter in dfmain, so eval the list, and so this should give us the filtered columns, and then we have this would be dd, because that's what we have labeled this here, and then we have these classes. So now when we plot this, this should be double d. So as we can see here, by removing so here we are looking at only these values that are not zeros, and when we look at those, now here we can start to see that some clusters or groups. So for example, these blue dots, some green dots, there is overlap, but then it is a relatively simpler in this case to maybe classify these data points as compared to what we have up here. And so that was the visualization part, and that concludes part 1 of this video. In the second part, we'll start looking at how to create features with the DataFrame DF main that we have, and then move on. So let's take a break. If you want to grab some beverage, feel free to do so. I'll be back in the part 2. Welcome back. In part 2, we'll now look at how to create features and process the data so that we can use it in the machine learning model. And in previous video, we saw that how removing some of the data or using only some part of the data from the data frame, we get much simpler clusters of data points, in at least as we see them in the 3D plot when we look at just 5 of those classes. Now, first item that we'll do is uh, we'll slice the data frame df main to create another data frame, and the reason for that is we'll use the df main and we'll use the df for separate purposes, and df is equal to df main, and here activity, and for this activity we are going to pick only couple of those as we have seen earlier. We'll use a, then b, we have p, r, and we have s. Then we copy that, create a copy of that. Now if you print df dot shape, so these are the number of records out of the 75,000 that will be starting with. So we started with 75, now we are at 21,000. So the reason why I've chosen only these 5 classes and not all of them, the first reason is if I tried running a couple of iterations, and if we pick all of them, the accuracy was much lower, and then in those iterations uh, I came to know that some of the data points, for example, if you think about it, walking on the stairs, the data points are a lot similar, and so it's different. It's maybe with the features that we have, it's difficult to differentiate between just walking and then climbing the stairs. The phone or the wrist would move maybe in the similar fashion, and that was one reason. And then if you think another reason could be, if you are sitting, just sitting, then your phone could be stationary, and so, and your hand could also be stationary, so the x and y, the coordinates could be closer to zero, because the accelerometer or the gyroscope may not be moving much. And so those activities I've tried to not include in here. And so these are the five activities that have that seems to work well with the linear models that we are trying to fit. With that, now let's go ahead and create some dummy variables. So get dummies, and this is for the rows, the columns that we created. We created a sensor column and we created a device column. So to convert those categories to numbers 0 and 1, we can use the create get dummies from the pandas library. So we'll create a copy of this, and then we'll df of sensor and device is equal to pd dot get underscore dummies, get underscore dummies, and then we have data is equal to df underscore sensor underscore device. And in here we have specified the two columns, sensor, and then the second column is device. And once we have that, uh, so let's see, sensor and device, this should not be a round bracket, it should be a square bracket. Okay, so we just pick those, and then columns is equal to, it's going to be the same, sensor and device. So with that, we can now look at the shape of this sensor device dot shape, and we get the same number of records, but then we have different, we have 4 columns there. So if we look at the head for that, this is the data frame that we have created, uh, which has ones and zeros for the sensor and device. We'll use that, we'll created it here, we'll add that to the main data frame later on. For now, we'll proceed with the DFR. So we'll create a new data frame DFR, and to that data frame we'll add the new features. So DFR is equal to df.copy and dfr.shape. So now we start working with this. We have the same number of records in there. As the first, we'll create features. So for features, I've tried several different iterations, several different types. uh, this could be statistical features, or those could be just features we are adding numbers, squaring them, calculating distances. Out of all the distances that I've tried, these were some that worked, and those are the only ones that I'm showing in this video. But if I think for practice, you could try other features, create features on your own and see how they work. uh, and if there are ways you could improve this model and include other activities in the model that we are working with. So let's create XYZ list. So this was the one where we have, so let's save that. So for I in range n, this is to create the XYZ list of features. So x0 to x9 and y0 to y9, z0 to z9. So for that, this is for loop plus str, and then the second one is y plus str, and then we have z plus str, So this gives us the entire range x, y, z list, print x, y, z list. So that's what we are after. We have these tuples in there, not tuples, but nested lists. And here we'll create a xyz transform, that's an empty list, and couple of variables, temp xyz underscore sum, that would be sum of xyz those values, then xyz prods, product of those, and then another variable will initialize is c, so 0 0 0, and then for product we are going to, so these are 3 zeros, so product we need 1, and so that's why the 1 is there, and then we have 0 for this one. So let's make this 1.0 so that it's a float, and then for initializing another variable zc is equal to np dot zeros, and this is based on the shape of dfr. So total number of column rows is the same in zc as the dfr, so that's 21,000. Now for xyz in xyz list, so each of what we are going to do now is pick each of these nested uh, lists and use them to create these features. So the first one, feature number 1, is we are going to get np dot, so we're going to squared values, so x0 squared plus y0 squared plus z0 squared, and we are going to do that for all the values from 0 to 9, and for that we are going to use column is equal to uh, dot join, and this is going to be xyz 0, and we have xyz 1, and we have xyz 3, sorry 2. Okay, and then we can create dfr column is equal to, and we'll add that here. So we have, first we'll have dfr dot lock, and we have xyz 0 and square of that, and copy that. So I'm taking the square of these and adding them up, and then taking the square root of that. So that's this, then takes that, and then take a square root of that, 0.5, and this would be 1, and this would be 2. So that's one feature where this is just the column name, and this is the value within that column. That's feature 1. Then feature number 2. So let's run this and see how that looks. I'm going to run that, and then we'll look at dfr.head and see what that feature is. So if you scroll all the way at the last of this, so these are the features that we created: x1 z1 through x0 y0 z up to this x9 y9 z9. So those are the features that were added by that line, and we can comment that out if those start giving us lesser accuracy. Feature number 2, and for this one again we are going to get squared values. So this is the square of all the values for, so here the squares were, so here we added the values for just the x0, y0, z0 separately, but now we are going to add all of them together. So that's going to be stored in the variable temp. So here we have dfr.lock, and then we have xyz 0 and square of that, and then I'll copy this because it's going to be repetition of the same thing. Copy that plus, and then copy that there. So this is going to be 1, this is going to be 2, and all of this will get added to the temp. So in each iteration, when we come into this, we have a different xyz. So first we'll work with x1 y1, then we'll work with x0 y0, then these 1s 2s 3 and so on. So all those values will get added here in the temp, and that will be the next feature. So the temp, once that is done, we can take a square root, say np.is sqrt and square root of temp, and then print type temp temp.shape, and we'll add that temp to the data frame. So here we have print, dfr and dist is equal to temp, and then we can print dfr dot shape dot shape, and get that dfr dot shape here, and dfr dot head 2. So when we run this, now we should be able to see the dfr data frame with this new new column, that new feature that we have created. So if we scroll all the way down, so that's the dist distance feature that we have, which is this last column. Let's create a third feature. So feature number 3, and for this feature we are going to count the zeros. So count zeros in x0 to 9, and then we have y 0 to 9 and z 0 to 9. So for that we'll write this. So m1 is the first variable, we have dfr dot log, and we take the xyz 0, and if that is equal to 0, then we are going to count it. So to convert that as type int, we are converting the boolean to number. So the zeros, the trues would be ones and false would be zeros. So everywhere there is a 0, so all the additions, the counts of zeros would be added there. M2, sorry, and we have M2 is equal to the same thing. So let me copy this. So that's for M2, and then same thing for the third one. And here we have M2, M3, and this would be 1, this would be 2. So once we have those, then we can say ZC is equal to plus equals M1 plus M2 plus M3, and that's the variable we initialized earlier. So I don't think we need this C. I'm going to get rid of that. Just need those 3. So with that, we can then add that to the data frame. We have dfr xyz underscore 0 dash 9 underscore zc is equal to zc. Now when we run this, we should get, so we don't need this part x, and so we have this another data frame that has the counts of zeros for the xyz from 0 to 9. And so what that could be an important feature, because it tells how closer to the origin the data point is as compared to other points that are away from the data point, away from the origin. So those are the features that we have created so far. And now these are some optional items that I've tried, which helped improve the accuracy. One is drop rows, and what this does is it removes data points for the gyroscope sensor, data for gyro. So most of the data for this is no longer there in the model that we train on. So here I'm going to create a d list is equal to, and what we'll do is we'll remove the same plot that we had created earlier, which is this one. So let me copy that and paste it here. So we have the uh, we start here from 3 not equal to 0, 4 not equal to 0, 5 not equal to 0, and all the way we are going all the way up to 9 not equal to 0. And within this, I'm just going to go ahead and add another item, dfr. So this is for dfr, so we'll change that now, x2, and this is so not equal to 0, and this needs to be ampersand there, and all the dfmain now need to be dfr, because that's the data frame we are working with. And the last one is this one. So with that, so what we are looking for is the data frames which have these values, which are non-zero values for all these columns, and we can use that as a filter, dfr, and then eval dlist. So that should give us dfr, and I'm going to save the index of this just in case if we use this earlier later on when we join the nominal value, the hot encoded values we created for sensor and device. Now we can get print dfr dot columns and dfr dot shape. So let's see what the syntax error. Okay, that's because there needs to be a colon quotation there. So we have 2548 records and 110 columns. So earlier we had 21,000 records. Now we just have 2,500. So because we used this filter, uh, we essentially removed most of the data from that we are working with, and we can see what the data now looks like. So fig is equal to plt dot figure, fig size is equal to 10 by 15, and here we can say sns dot heatmap dfr dot block, and we need to check what columns these are. So here we don't see all the columns. So what I'm going to do is go back up and run that cell again. So this one. So that should allow us to see all the columns. So dfr dot columns. No. Okay. So we at least have this initial one. So 0, 1, 2, 0, 1, 2, 3, 4. So we are at 4. So this would be 1 plus 4. Then from there to 30 plus 4. And we have cmap is equal to binary. So when we run this, see what the error is. Index cannot do slice indexing on index with these indexes. Yep. Because that's lock. Now when we run this, we should be able to see that those blank spaces are now gone. So this could start at 0 instead of 1 and work. So in the previous plot, we saw that there was the gyroscope readings had zeros for all the way from x4 through x9, y4 to y9, and so on for z. We removed those rows, and so now the data frame is much denser and it has less zero values in the data frame, and so that would help us um, train the model better. So let's now see which rows did we remove. So which rows were removed, and you can say dfr dot group by, and we have sensor, sensor, and then count. And we can see that there are only 4 rows for gyroscope readings, and rest of them are from accelerometer. So similar to this, we can also check for what device. So instead of sensor, we can type device. And here we can see there are around, most of them are for watch and relatively less from the device phone. And finally, we can also look at activity. And we can see that for the activity R, there are lesser data points, and there are a lot more for the activity B. So with that information, we can now proceed to uh, cleaning the data frame and getting in the final form. So first we'll drop the columns that we do not no longer need. Drop file, activity, sensor, device. So dfr is equal to dfr dot drop, and here we can specify the column names: fname, sensor, and then we have device, and we have class, axis is equal to 1. So those are the columns that we no longer need, and so we can delete those. And apart from those, then the next item that we can look at is y. So we can split the data frame now. So split x and y, and that should be okay. So let me go ahead and put that as a separate subheading. Okay. So for x, first we'll work with x. So x is equal to dfr dfr dot columns, and then within this there is the mask dfr dot columns dot is in, and this is activity class we don't need because we have dropped it above. And then that's the x, and then for y is equal to dfr activity. So I'm going to do print y dot sort underscore values dot unique. So these are the classes, these are the activities that we have, a, b, p, r, s. And let's look at the columns. So let's go back up and let me run that cell again. I don't know why that is not working, but anyways, so that's those are the columns we'll be working with. And now for features, we need to remove the features that have zero variability. So features with zero variability, and in this case we just have numeric features. So x is equal to x. So we first need to get the variability. So x dot var axis is equal to 0, and that is 0. So when we look at this and when we run this, so let's get a shape of this. I'm going to put that in a variable, say a is equal to this, a dot shape. We have 105, and we look at shape of x, we have 105. So we are getting that for each column there. And so put that in here in parentheses, then dot values, then put that in a square bracket, and then x dot columns, and then that would be the x. So now if we look at print x dot shape, x dot head, so these are the columns we have. So we started out with, I think, our dfr dot shape, we had 106, so we lost 3 columns in this case. The next item is removing collinearity. So that is to remove features that are correlated. That is, if x increases, y increases, or they move in the same direction. So for this, there is a function. So remove correlated columns or features, and we do this by setting a threshold value to cut off and the r square value. So we'll set it at 0.7 because that seems to me like a moderate correlation begins there, and that correlation is kind of depends on what type of data you are working on. So in this case, 0.7 should work. Columns, and then print. So we'll print the value before and after. So number of features before, and this would be length columns, and then for this is similar to what we used in the previous video on mushroom classifier. For I call in columns, we have if call, so we need the columns to be different. I call, then here we calculate the r square value is equal to np dot correlation coefficient for x column and xi column. And once we have the matrix, we take the cell from that, square that, and if that value, then if r square value is greater than or equal to 0.7, again this is arbitrary and it could be any other value, then calls dot remove, so we remove that column, and we can print number of features after, and here we can specify length columns and return columns. So now we update, keep only non-collinear features, and for this new underscore columns, we're going to remove underscore, I'm going to call the function collinear columns x, and run this again, and that's the reason is because there would be some columns still collinear, so the second pass should remove all of them columns, and this would use the only the columns that are from this new set. Run that, so this should be square brackets. Okay, so we are left with around 51 features. We started out with 100, so we lost around 50 features there. So x is equal to x new columns, so that's going to be our new x dot shape with 51 features. We can visualize that, so visualize figure is equal to plt dot figure, fig size is equal to 5,3, x underscore corr is equal to x dot corr, and then we square that, and we use the sns dot heat map x underscore corr. The map is equal to viridis, and let's see what the error is. Okay, this made a mistake. Cmap, and as you can see, the yellow dots are only along the diagonal, so the value of 1. Others are good. So we look at x dot columns now, and so these are the columns we have. We lost the sum product columns. We do have the dist, and we have some other columns. We have this x3 y3 column in there. Now we can transform this data set further by using transform distributions, and the reason why we are doing the transformation is because some of the data could be skewed. So if you look at plt.hist, and if you look at x0, as you can see, it's skewed. It has the right tail, and so that can be fixed using the transform, and we'll do that, and after that we'll do the scaling. So df q underscore transform column xx is equal to np dot array column dot reshape -1 1, and I'll use the quantile transform. Rng is equal to preprocessing dot quantile transformer, and this n underscore quantiles is equal to 100 output underscore distribution. We need it to be normal, and then the random underscore state is equal to 0. We could also use R transformer pre-processing dot power transformer and method. The default method is Yo Johnson. Comment this out for now, but you could give it a try running this transform and see if that changes accuracy of your model. Xx is equal to rng.fit underscore transform, and then this returns xx. So that's the function, and we can use that now to transform the columns in x. X underscore column is equal to x dot columns, and then for call in x underscore column, x call is equal to q underscore transform, and this is going to be x column. So there's an error, name rng. Okay, so that's my mistake. It should be fit transform. And now if you look at x dot shape, this, and now if you plt dot hist x x0, the same plot we had above, it looks like this now. So it's more towards normal distribution. Next we'll run standardization. So so in this case we may not I mean, it's not needed that we standardize because the transformation would do that for us, but I'll add it here anyways. Pre-processing dot StandardScaler. So you could try running the code with and without this transform and see if it changes the score. X is equal to scale transform x, and you can print x dot shape and x, or maybe one value of x, and pre-processing. So that's those are the values we have. They look, and they should be around mean of 0. Now the next thing we need to do is join the device and sensor columns. To join the sensor and device columns. So these are coming from the beginning when we created those values. So of ones and zeros, we'll add them here. np.array x, we convert that data frame to array. df underscore sensor device is equal to df underscore sensor underscore device dot alloc, and here dfr dot index. So we need to use the same index as for that. We have the same rows. df underscore sensor device is equal to np dot array. Now we convert it to the array and then concatenate that with x. Concatenate, and this is df underscore sen underscore dev. X is equal to 1, and we print x dot shape. So now we added 4 rows, so we had 51, now we have 55 records. Finally, before we do the trend test split, we can check the counts of the groups again. So check group count. So we know what is in, how many would be in each. So class underscore index is equal to y dot. I'm just getting the values for index from y and use that in this array with df dot alloc y dot index and dot group by activity, then count the same activity dot count, and we have around, so these are the values we have for each of the groups, these many number of records. And if we want to, t is equal to this, print t, and we could also get print t dot sum or sum, and we have 2548 records. That's what we have above there. So that concludes part 2. We'll take a short break and we'll continue working on the modeling part. That's the part 3. Welcome back. And in part 3, we now have the data set ready, which we can split and uh, run our training models on that. So let's split the data set. Split, train and test set. And here we have the same standard method that we have been using, x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split. And here we have x, y, and I'm going to use shuffle is equal to true and stratify is equal to y. So that's the y we have above. And with that, we'll print the values. So print x x underscore train dot shape, and then x underscore test dot shape. And we have around 1911 in train and 637 in the test set. So let's now create the models, and as before, what I'll do is create a function that runs and predicts and plots everything for us. We don't have to type it over and over again. The fit underscore predict. So this is same as what we had in the previous video on mushroom classifier. clf.fit x underscore train, y underscore train, and then we calculate the pred, so that is equal to clf.predict predict, that is x underscore test. And once we have that, we can go ahead and calculate the accuracy matrix dot accuracy underscore score, and that's y underscore test, y underscore pred, and then print that out. So accuracy score, and here we use float, so percent 24, and this is the accuracy. And we can also get the confusion matrix, so matrix dot confusion underscore matrix, again the same, y underscore test, y underscore pred, pred, and then we have sns. We can calculate plot the heat map of the confusion matrix, and just use binary so we can see the dark and light spots easily. plt dot show, and then also print the numeric values for the confusion matrix, and then return accuracy and confusion matrix. So that's the function. Now comes the part where we are going to stack up all the models from linear models, and then we'll run them in a for loop. So model underscore list is equal to, and in this we are going to put all of these in a tuple. So linear underscore model dot logistic regression and max iter is equal to 1000. So I'll encourage you try different parameters here, see how that changes the fit of the model. Elastic net. So solver is equal to SAGA. You can start with the basic default and then change and see different combinations. So this, I'm setting this to 0.5, and so that is the name is logistic regression. So that's the first one. Then the next one is logistic regression classifier as cross validation. So linear underscore model dot logistic regression CV, and for this we'll set CV of 3, max underscore iter is equal to 1 e3, um, uh, 5 e3, penalty is equal to elastic net. You can also have L1 or L2, and depending on that this solver may be different. And here we have L1 underscore ratios, so you can specify a range of ratios here. So I'm going to start with 0.25, 0.45, and maybe 0.75. And after this we have random underscore state is equal to 0, and finally the name, and this is logistic regression CV, comma, and after this we then have ridge regression. The linear underscore model, forgot the L there, model dot ridge. I said ridge regression, what I meant is ridge classifier. So ridge classifier, and this random underscore state is equal to 0. This is ridge classifier, and then we have linear underscore model dot ridge classifier CV, and for this you can try different alphas. So alpha is equal to 1e minus 3, 1e minus 2, 0.1, 0.4, 0.75, 1, that should be enough. And then we have a ridge classifier CV. After that we can try SGD. So linear underscore model dot SGD classifier, and the random underscore state is equal to 0, and the name again is SGD SGD classifier. And after this we have the perceptron, linear underscore model dot perceptron, and again for perceptron random underscore state is equal to 0, and name would be perceptron. Moving on, I'm also adding SVM here, a linear SVC random underscore state is equal to 0, and linear SVC support vector classifier, and then we have linear discriminant analysis. So linear discriminant analysis. So this is LDA. Then we have quadratic discriminant analysis, and this is QDA. I'm using the default values in those, and also we missed the linear class passive aggressor, linear underscore model dot passive aggressive with double S, aggressive classifier, and here's is setting the C to 0.5. Random underscore state is equal to 0, and this is passive aggressive classifier. And lastly, we have not worked on this, but adding this here just to show that how it works in comparison to the linear models, how powerful that is. Random underscore state is equal to 0, and then random forest classifier. So that is the entire list, and with that we can now run a for loop. So results, we'll put all the results in here. For CLF, name in model underscore list, print, just creating a line there, 25, print name, and then again print np.sort. We'll print the activities, dfr activity, and that is dot unique. So we have those printed there, and then also what those activities mean for reference. A is walking, then we have B is jogging, and then we have P is dribbling basketball, and then we have R is clapping, and then we have S is holding clothes. So those are the classes and their names. Plot another line there, print another line, 25, and then we can have the results. Append fit underscore predict CLF, and then we have the name that goes in there. So with this, let's end this by printing another line. So underscore, maybe a hyphen is fine, 25, and then add a bunch of new lines there. Okay, so I think save the file, and these should now run all these classifiers through this function using the X train, Y train we have, and we should see the outputs below. Let's run this and see what we get. We get an error. So let's see what the error is. Model logistic regression, unexpected keyword solve. Oh, that's right. Missed. Maybe there are a couple more errors in there. I don't know. Random is not defined, and that's because random forest classifier or random forest. Let me go back up and copy this, and then just type that here, or just paste that here as well as a typo in that. Okay, so it's starting to run, and we'll wait and watch. Okay, so we have the regular logistic regression giving accuracy of 96, and as you can see, this is the confusion matrix. The diagonal elements are correct classifications, off diagonals are incorrect classifications, and we can see that the A would be the walking, and we can verify that later on. So 0 would be for walking, we have 96. Then 5 of the jogging are misclassified here and as walking, and that makes sense because it's similar. Then we have these bunch of uh, holding close activities misclassified, but it's still doing a pretty good job. Here we can once we this might take a while for the cross validation to run. If it takes more than couple of seconds, I'll cut this and join back after the entire code is run. So meanwhile, let's look at this confusion matrix. You can see that again these are incorrect classifications for walking, clapping. So R. So I think this one should be for clapping number 3, which is this one, and it was correct classification. So for clapping, it seems that only the wrist would be moving, so your watch, the data from the watch and not the phone. Maybe that helps classifying it correctly in this case. And then we have this 181, which is for the basketball. There are a couple misclassifications there. So I'll stop this video now and come back when this entire code is run. Welcome back, and here we have the code that is run. Let's look at the output. Logistic regression, we have 0.96. Then for logistic regression CV, it's much lesser, so this could be overfitting the one above. Rich classifier is much lower. Rich classifier CV, again same 0.92. SGD is 0.94. We have perceptron, again same 0.946. Linear SVC is 0.95. LDA 0.93. I was hoping that QDA would work better than LDA. It's 0.91. Maybe if some tweaks are done, this value could change drastically. Passive accuracy is 0.94. And as you can see, random forest does the best. That's 0.97. That's just to give you an idea that there are other methods outside linear method that we'll be looking forward to learning in this particular series. So for now, the linear models, I think they are doing pretty good job. Most of them, I think all of them have accuracy above 90 for this particular data set. Now, before ending this particular part, what I want to do now is go back and change couple of things in the the features that we have created and see how that works. So what I want you to do for practice is go back, change the features, create new features, delete some features, add new rows, delete rows, create visualizations, and see if you can find anything new, or if there is an alternative way to work this problem, if you can improve the accuracy, or find out what happens, what can decrease the accuracy. That's also another way to learn. So all these uh, variations are what will help you uh, analyze new data sets, because there could be some commonalities between different projects. So here what I'm going to do now is remove this feature. Before doing that, let's go back up, and here we have been using dfmain, which is just these classes. What if we use all the classes. So df is equal to dfmain dot copy, and I'm going to comment this one out. So now we have all the classes. Okay, so uh, I'm expecting that because we have all the classes, the data is going to be something like this, and it's going to be difficult for the classifiers, linear classifiers, to classify these, and the accuracy may drop substantially. So let's run this. And again, this is copy of df main, so we are good there. We can use that. We now have 75,000 records, and that's our sensor. And df, this comes from df, so we are good here as well. dfr, we have 75. Now we create these features, and we are with 75. And here we now uh, this will change, this will remove some features. So from 75 we dropped to 4,399 here. And if you look at the columns, we have prod and sum columns now included, which were not there previously. If we look at this, so this looks similar to what we had before. Again, now if we look at the counts, all the gyro readings, most of them are removed. And here one issue is that we now have these features. These are the features which are more less active features, where you would think that the gyroscope measurements are closer to 0, and those are the ones that are affected when we run that filter, this filter right here, and that's why these are gone. And now if we look at, we drop those, split, and then we can go through removing these 0 variables, then go to collinearity. So now we just have 50 features, and we check that collinearity is good. And here we see that these are the features we have. Now we look at the transformations. Again, the transformations look okay. Now go through the standardization, and now look at the count of groups. So some groups, so these groups are still there, which are very, very few, and this is a very high chance that those could get misclassified. Now we can run this. Now we get an error because for stratifying, y has only one member. So I think the one that we saw earlier, but in this case we are using x, so I don't know why this is based on the values for y, which is using okay, so this is y index. Oh, maybe right, because we are splitting this, and that's why it's not going to work. So I'm going to comment that out just for sake of running this, and maybe we don't need that comma there. So we run this, so that's the split. And now remember, this we were at 96%, and now when we run this, let's see what values we get. And as you can see, there are a lot more classes. So that this is incomplete right here. So I'll let this run, and after this is run, I'll come back. Okay, it looks like it's already there. So the logistic regression still gives accuracy of 0.84, which is, I think, still reasonable given the features we had. So this is completely misclassified. This feature is completely misclassified. This is misclassified. These are so one 2, 3, 4, and these would be the ones that have less to no feature, less to no data points in there, which were these right here. Um, n- and then these are 73, 305 correctly classified, 100, 103. So overall, it seems reasonable. The numbers would be lower because we have so many classes. So even if there are one or two misclassifications from each of them, they would add up, and that would bring down the accuracy. Now here we have an error. The least populated class has only one members, which is less than the n split. So maybe that will not run. So this was not converged. So what we would need to do is, so let me go and stop this run, because we need to increase this iteration. So let's make this 5000 5e3, and then this is, I'll stop this because we don't have enough uh, number of records in each class, so probably won't do that. And then run this now with just logistic regression without logistic regression CV, and we have increased the max iteration. So what that could mean is the it will change the accuracy. I'm guessing it will go up, but we'll see. And after that, I'm expecting that the random forest classifier still would perform better than other linear models that we have. It's the tree based classifier. So let's see what output we get. So we have 84.84 for logistic regression. Then rich classifier is much lower, 0.77. Still, it's still, I think it's reasonable. Maybe room to improve if there are additional features that are more relevant. SGD 0.8, perceptron 0.7, linear SVC is again above 0.8, linear. This did not work. One sample, so QDA won't work, and the one that remains now. So let me comment QDA out. So we just have then passive aggressive and random forest classifier. So when you're trying to practice with this data set, what I'd suggest is, instead of running them in this loop, you could pull each of these classifiers out and then uh, run different variations of iterations, penalty, solver, L1 ratio, and see how that affects the score, and then go back, change the features, and see how that affects the score. So let's scroll down, all the way down, and here we have the passive aggressive is 0.76, random forest is 0.88. So till uh, till I was thinking it will reach 90, but it's at 0.88. So better than linear, that would be expected. Now what we can try to do is, uh, instead of looking at all the features, uh, we'll look at just those five, but then we'll all the classes, we'll just look at those five classes that we did in the very first run, but then we'll remove some features. So let's uncomment this line and then comment this one out. So that's the one we need, and then we have this is the same. Here what I want to do is remove one of the features and see how that affects. So we run this and then run everything again and collinear and transformations there, standardize, join these values, So now we just have these 5 and we can stratify. So I'm going to remove that, there, run this again, and we can uncomment this because we have enough uh, records for each class, and run this and see. So as you can see, by removing just one feature, and this accuracy jumped to 97, and that's a big change. So that is to tell you the importance of feature selection. Here we did not do any automatic feature selection, but in future videos we'll look at how we can find the optimal features to be included in the model. And here, an important point again to note is that choice of features is important, and the knowledge required to choose particular features or create new features comes from the knowledge of dataset or insight of dataset. A simple example would be uh, trying to understand that walking, the data collected by the sensors for a walking activity could be similar to the data for activity of climbing chairs. So in both cases we are walking, it's just that we are climbing up the stairs. Maybe there's not a whole lot of difference. Similarly, sitting and typing could be similar. Maybe the hand readings for the wristwatch could be different than sitting, but the readings for the phone could be similar. And that's another kind of way to think about the data while either creating new features or uh, removing any features or data. At the same time, we want to remember that data can contain noise and outliers. So visualization helps in spotting those, and then you can write a code to remove those outliers from the data set. So while this is running, here we can see that there are there are fewer misclassifications than the run that we did in the previous case. So after this is run, I'll cut the video now and come back after this run is done. Welcome back, and here we have the values for logistic regression is 0.797, and then rich classifier has now improved, it's 0.94. Rich classifier CV is the same. HGD is much higher, now it's 0.96. Perceptron at 0.95. Linear SVC 0.97. LDA and QDA. LDA is much higher, 0.95. QDA is lower, 0.93. Passive aggressive is 0.94. And then random forest is at 0.978. So that's much closer to what we have here in logistic regression. So that was it for this video. I hope in this video you got a new experience on implementing whatever we have learned in pandas, numpy, and scikit-learn linear models into a real world example of a much larger data set. And uh, as you probably have realized by now that most of the time that more than I'd say 70% of the time you spend on getting the data, cleaning the data, and processing the data to get it into a format which can be used as an input to the machine learning model. So the machine learning part in this case was just these two cells. That's it. And the tools or the series so far what you have learned in the videos will um, help you guide on which of these parameters to choose and why, and it'll also give you intuition on how to create new features or kind of visualize or think about the cloud space of points such as shown here, and the distances between the points and how they affect. So that's how going through the background of each of those methods helps in this case. Additionally, here we saw that this was just one example of visualization. I'll encourage you to look at visualizing this data from different angles, uh, with plotting combinations of different features and see if that has any effects, or maybe adding some new statistical features to this data set and see if those help in uh, improving the accuracy or if decreasing the accuracy. Please like, share, and subscribe. If you have any comments or suggestions, please let me know comment section below. I hope this video was helpful to you and you learned and got an hands-on experience on how to apply machine learning models on a real-world data set. In this case, biometrics activity classifier. I hope to see you all in the next video. Thank you.